Hello everyone, welcome to this tutorial. I'm James. Today we are going to working on a very hardcore but also extremely interesting project, ESP32 came AI gesture recognition and edge computing. We will start from scratch, training the neural network step by step in Python, and then pack this AI brain into a microcontroller, achieving real-time gesture recognition without any network required. So let's get started. So before we dive into practical applications, many people ask, with cloud computing so advanced now, why go through the trouble of running AI on microcontroller? So there are three irreplaceable core advantage. So first, the privacy and the security. So when performing image recognitions, the footage captured by the camera doesn't need to be uploaded to any cloud server, and all computation is done locally and this small chip. So the data stay within the chip rich, ensure 100% privacy. And the second reason is low latency because it doesn't rely on the network connections or wait for cloud server updates. So the chip immediately perform inference local upon captured image, allowing for extremely fast and real-time recognition responses. And the third is the low cost. This ESP32 came chip costs only a little over 100 NT dollars, and its power consumption is extremely low. So compared to buying a high-end GPU computer costing tons of thousands of yen and consume a lot of power upon startup. So this low cost, low power edge computing architecture is the ultimate solutions for deploying AI on a large scale to every corner of the world. So having reviewed the advantage, my plan is to use ESP32 and camera to recognize the rock, paper, scissors gesture. So let's review the hardware configurations and communication architecture used in this project. So first, there is our main component, ESP32 came, which carry out the scaled down neural network model. And the next is the camera modules called OV2640, responsible for capturing real-time images of the rock, paper, scissors gesture. So how do we present the results to user after the chips calculated? So here we adopt a dual core architecture. On one hand, we stream the real-time images to the browser via Wi-Fi. And on the other hand, we can use another core for AI inferencing. Finally, we connect the computer via Type-A cable directly to accurately reading the lines by lines to 5, 4, 3, 2, 1 countdowns and AI recognition status and final report of remaining rain for successfully identified character in the computer web browser and serial monitor. So this golden combo of hardware and communication is practical battlefields for our entire videos today. So what will we exactly cover for this tutorial? So first, we will cover the dataset preprocessing, and we will show up how to train the models and how to quantize the models, which is to compress the model to a smaller one. And we will show how to deploy the model to the MCU. And the final one is we will show how to optimize the models, including the CPU multitasking and the RAM management, which is the memory management, to trying to figure out what is the best of the models and how can we push the model to the limits on small devices. So what we learned from this tutorial? So first, you will learn and understand how to train your own models, and then it's know the exactly process for deploying the models on an embedded device. And the case in here is ESP32, as I mentioned, and know how to do the CPU schedulings and the practice of the CPU multitaskings. So I think it's a very comprehensive tutorial for you to learn how to train the models or deploying a tiny ML models on edge embedded devices. So let's dive into it. Now we are kicking off the chapter 1 of our tiny ML journey. So before we touch any hardware or microcontroller, we need a brain. We need a models. So in this chapter, we will walk through entire AI pipeline from how to grab data, how to clean it, how neural network actually learn behind the scenes without getting lost in pure math, and finally, how to evaluate and explore our model. So let's start it. All right. When we are about to train the models, the absolute first and the most important step is to figuring out where to find our data. Of course, you can select it or collect it by yourself, whether it's logging data manually or taking your own photos. But nowadays, there are tons of resources available online that we can search through. So here, I highly recommend a very useful public dataset website. It's called Kaggle. You can find a massive variety of open source dataset there. And but of course, remember to always cite your resources because the dataset are the result of others people's hard work and dedication. And the next step is the data categorizing. This concept is highly important because how you split your data directly determine whether your models become truly smart or it just memorize the answer. So now when it comes to the data splitting, the best practice is in standard machine learning isn't just split it into two part, just like the training set and validation sets. It's actually divided into three. There are the training sets, validation sets, and the test sets. So let's use student taking a big exam as an analogy. So first, the training set is like your textbook and the practice problems. This usually takes up a largest proportions, around 70 to 80%. It is what the AI used to study and look at the answer. For example, the AI will study these 700 hand gesture photos while checking the labels to figuring out the patterns of rock, paper, or scissors. And the second, the validation set is like the mock test or the practice quiz. So the actual taking up about 10 to 15%. We use the mock test score to fine tune our model's architecture. If you notice that AI accuracy dropping during these quizzes, you will know, oh no, the models might be too complex and it's starting to memorize the textbooks, and it is what we call overfitting. And the test set is the actual final exam. It takes out about 10 to 15% of the data. So it is used for final evaluation after the model is fully trained and all the parameters are locked out. The AI cannot sneak a peek at the data for even a single second during the training. It's only brought out at the very end and test how well the AI perform in the real world. For instance, when you point ESP32 came at your own hand. However, in many simple machine learning workflow, people often blend validation set and testing set together. But in rigorous engineering, they are strictly kept separated. Okay, so before we get deeper to it, we will do some turn explanation to these three terms. It's very common to see when you in the machine learning field. There are three collective known as deep learning frameworks. So simply put, they are high-level toolkits that predefine extremely complex mathematical formula such as matrix multiplications, convolutions, and backpropagations, which we'll discuss it later. Without them, writing even a simple 3.3 convolutional layer will highly require thousands of lines of low-level code in C++ or Python. So people may ask, are Keras and TensorFlow two separate things? Actually, in today's, Keras is part of TensorFlow because Google officially acquired Keras. And PyTorch was developed by Meta. From these inceptions, it directly competes with Google's TensorFlow. So a drawback of the TensorFlow in the early stage is it uses a static graph. You must define entire neural network architecture beforehand, and once the trainings begin, it cannot be modified midway, nor can you use Python print functions to see what happens and see the numbers the metrics have become. And that makes debugging more difficult. So the PyTorch is another alternative because it uses the dynamic graphs. Like the regular Python code, you can print out the result of each convolutional layer using print functions as you train the models. This what you see is what you get characteristic has made PyTorch a sensation in university, research lab, and academia. Now, the vast majority of AI papers, including ChatGPT's LLM models, are written in PyTorch framework. So we need to decide which one to use. So if you working with a hardware-based AI, then use TensorFlow because Google's TensorFlow Lite is a very powerful toolkit. Uh, is a very powerful toolkit, and TF Lite is absolutely leader. It can deploy the TinyML on MCU. It can compress the model to the smaller one. They have very mature pipeline to quantizing Keras model or TensorFlow model into integer 8 and then export them to as a C++ hexadecimal array. But if you want to work with the latest AI models, for example, the image recognitions, then choose PyTorch because currently 90% world newest and top tiered, as I mentioned, like ChatGPT, open source AI project are in PyTorch format. So as you can find them on GitHub. So that is the difference between TensorFlow and PyTorch. However, if you train using PyTorch, you can still convert it to TF-Lite, but you will have to go through the entire painful conversion hell from PyTorch to ONNX, we will discuss it later, and to the TensorFlow framework and the TensorFlow to convert it to TF-Lite. So what exactly is ONNX? So ONNX is like the universal language, just like English of this world. To think of this scenario, a Japanese person is like a PyTorch, and a Chinese person is like a TensorFlow. They cannot be communicate with their own mother language, but when they're using language, they can very smoothly to understand what they want to express. So this is a very simple analogy. In previously, engineer had to manually rewrite the model using another framework while working with mathematical formula. This is definitely a disaster for each tech world. To solve these problems, the giants like the Microsoft and Meta jointly developed ONNX, which is called Open Neural Network Exchange, to solve these problems. However, our project will not use ONNX because we haven't choose the simplest way and the most straightforward path, which is developed is all done within Google's framework. We will use TensorFlow and transfer it into the TF-Lite. Therefore, our project will not follow this route. Yep, so before we start in writing Python code, we need to establish the holistic mindset. So please look at this roadmap. This is the learning path we will tackling step by step. First, The first stop is data preprocessing and augmentations. Here we will discuss how standardize the photos we have and use geometric deformations and lighting effects to artificially expand and enhance the database, data sets, laying a solid foundation for AI. After acquiring the data, the second stop is the model architecture building. This is the core of neural network, and we will break it down into two key points. The first is simple explanations of the CNN architecture, and we will showing you the inner working of convolutional neural network in the most accessible way. And another is the forward pass and the backward pass and the loss functions, which is the closed loop of the neural network performing task, scoring, and self-correcting parameter in background. And after the model's training, the third stop is evaluating the results. So we will use practical example to break it down the learning curve and the confusion matrix. It will teach you directly to understand learning curve graph and confusion matrix. This mistake note will allowing you to instantly see if your AI is truly intelligent or just memorizing the answer. The last two stops are the concluding and practical applications. We will move on to export the model, seeing how the packages, the compress, and how to convert the brain data, what we just trained to a smaller one models. And finally, we will get into a real examples to taking you directly into the world of code and hardware developments, putting all the concepts together. And I think it's a very useful tutorial and you can learn a lot from it. So let's get into the first stop, the data preprocessing. Okay, so the image recognition project, although these two steps which I mentioned is the data preprocessing and augmentations are both processing images, but their purpose are completely different. So the preprocessing is to make the image to meet the input specifications of the models, and image augmentations, or you can simply think is like image enhancement is to create more data out of nothing to prevent the models from overfitting. So the first we see the data processing, which is necessary procedure before all images enter to the models. It includes three core actions. So the first is resizing, where we need to capture a variety of original images with the camera and scales them all to uniform specifications. And the second is the color space conversion, which converts color image to grayscale images to greatly reduce the subsequent computational burden. And the third is normalization, or you can think it as a standardization, just mathematically translate or scale the pixels value to make it easier for models to converge. And the following role of the augmentations is a special medicine that makes models smarter. It makes the database come out of nothing through a random deformations of geometry and the light and the shadow, such as geometric rotations, just random rotate or the random flipping, and translation or shift, just random to shift the images to slightly different from its origin, which can ensure that even if the gesture is crooked or reversed or not replaced in the center, the AI can still recognize it. And the light and shadow, like a brightness or contrast and the noise injections, can stimulate various room lights and lens noise in reality. So, however, the above data enhancement method are advanced image processing. We will not talk about it here because that will involve too many very complicated mathematical things, so we just list them for you to know. So here we are, the model selections. So with the data prepared, the next step is to select the suitable AI brain for our gesture recognition project. When facing image recognition task, the industry typically offers several common models architecture to choose from. So first is MLP. Using this traditional architecture to process entire image pixels would result in so many weight parameters that it will overwhelm entire memory, and it will also fragment spatial features, making it impractical. As for mobile net2 v2 and RaceNet, while incredibly powerful, but their size is simply too large for embedded chips with only few hundreds KB of storage spaces. And layer 4, weighing computational resources against recognition capability. Our project automates its CNN. It's also called Convolutional Neural Network. So CNN's unique local sensing and weight sharing mechanism is practical, tailor-made for image processing on microcontrollers. It can accurately capture the edge features of an image with a very small model size. So this winning CNN, how exactly does the internal architecture work? How are the building blocks stacked together? On the next page, we will dive into to core to provide a detailed structure breakdown. Okay, so let's directly look at a classic CNN architecture diagram. On the far left is our starting point, the input layer. The diagram shows a colorful photos of the sailboats representing the raw image data we will be feeding to the AI for recognitions, but this is not the example we will use for the further project. This is just the photos I found in the internet. So after the photos came in, the first stage is convolutional layer. You can think of the convolutional layer as a bunch of the block filter like this. This is just like a block, and the AI will use several different small filters to moving across the beautiful sailboat photo, producing several new images, specifically recording edges and features. But with so many features, what if the computation's load is too high? So remember, we only have a very small MCU. They only have a limited memory storage. So the next steps comes to first subsampling, or you can call it pooling layer. So this pooling specialty is to intense compressions. It proportionally reduces the size of the feature. So you can see the size, or the size of the image is greatly reduced. So reduce the size of the features images to just captured, leaving only the most important and obvious core features. Then it combines the technique to repeat it. So we back to the convolutional layer again, and the photos will enter to the second round of the convolution layer to extract more complex contour features, then pass through the second subsampling layer or pooling layer. And the second compress is performed after the two rounds of extractions and compressions. The original sailboat photo has become a very small one and feature-rich three-dimensional images in this computer eyes. But remember, this process or this procedure don't show up the data preprocessings as I mentioned before. So just remember, we have a step in this point in here to do the data preprocessing. Okay, so now for the main event, how do we get the computer to make selection based on these features? Notice that this images has two full connected layers. right here. So um, um, okay, so notice that these images have two full connected layers before entering the final output. In the first connecting layer, the computer forcibly strengthens the previous shrunk features enhanced into a long neuron for initial features specializations, and then it connect to second full connected layer. These two dense packed intersecting line are like the brain multiple thinking circuit, perform a deep and complex comprehensive vote on all the features captured. So after these two layers of four connected layer of thinking and filtering, the final stage is the output layer. So at this point, the multiple thinking circuits submit or transmit the final voting energy to the corresponding category. If it finds that the features of highest score is captured, it will accurately output the boat identification like this one. It's very small, I know, but it will accurately output the boat identification result on the far right. In this way, the entire journey of the color just completed. Okay, so the next part is the real core of how entire neural network works. We will look at the forepass, loss functions, and backward propagations. These three steps are actually a completed closed loop for AI from guessing it to correcting it. So the first step is the forepass. It's just for inferencing. So this process is very intuitive. It's a matrix calculation journey where data flows from input to output. When we input the pictures of sailboat, the previous example, the pixels data of pictures begin its journey. The lines are extracted through the convolutional layer and compressed through polling layer and then synthesized through fully connected layer. At this stage, thousands of tiny parameters in the network move together like complex gear, ultimately transformed to probability for three categories at the output layer. In other words, forward propagations is essentially the AI's effort to calculate and submit the predict number based on the current hardware state. And the next step is after we submitting its answer, AI doesn't actually know how accurate it is, so this is where the loss function comes out as a gear, as a grader. So the loss function essentially performs as a rigorous mathematical comparison between the answer calculated by AI during the forward pass and the actual labeled answer. So in classification tasks, we typically use the cross entropy functions. If the actual answer is both and the AI probability of guessing about is high as 99%, the loss calculated by the loss functions will be close to zero, meaning there is little to deduct. However, if the AI guesses the bird when it's clearly a boat, the loss score will skyrocket. The loss score tells AI how far it is from the perfect answer. When with this loss score, the most amazing thing happens: the backward propagations. For the AI to improve, it must know where to when run. Backward propagation is like completely reverse the forward pass. So starting from the rightmost output, it works backward using a chain rule of calculus. I know it's very complicated, it's just mathematical things to calculate how much each neuron and each convolutional kernel contribute to the final loss score. Mathematically, it is called the gradient calculations, knowing the gradient. For example, knowing the directions of modifications, the AI can fine-tune the weights of all the gear within the network through the optimizer. So if the ship getting wrong this time because a filter for capturing lines was too far to the left, the backward propagations will slightly adjust the filter's parameters slightly to the right in backward. So therefore, the neural network training works just like this. For each image read, a forward pass is performed to calculate the predict value. Then the loss function is scored, and finally the backward propagation is used to correct the hardware parameter. So these three steps are repeatedly thousands times and during the training until the loss score is reduced near to zero. So at this point, the AI brain can understand colorful sailboats or rock paper scissors is truly born. Okay, so after the model is trained, how do we know if the training is well? The most intuitive way is to look at this two learning curve graph. So let's look at the accuracy graph on the left. So the horizontal axis represents the numbers of training epochs, and the vertical axis is accuracy. There are two lines. The blue one is the training accuracy of AI reading the textbook, and the orange one is the validation accuracy of the mock test. You can see that in the first 5 epochs, both lines rise rapidly, like climbing a hill, indicating that the AI is quickly absorbing features. And around the 20th epochs, both lines stabilize between 0.5 and 0.8. This is a beautiful graph because the blue and orange line are very close together. If today's blue line soared to 1.0, but the orange one remains stuck at 0.4, it means the AI has completely overfitted. And having seen overall progressive trajectory, this one, if we want to pinpoint which specific questions that AI is mostly like to confuse, we need to look at this confusion matrix. This graph is essentially the AI's error log. The simple trick to look at this graph is to stare direct at the dark blue diagonal line from the top left to the bottom right. The horizontal axis represents the AI's prediction, and the vertical axis represents the actual answer. The number on the diagonal represents the numbers of times the AI guessed correctly, this 3D one. And for example, the actual number of cat, and the AI guess is a cat getting it right 8 times. And the actual answer is dog, and the AI guess is a dog getting it right 10 times. And the actual color is horse. Oh, sorry. The actual answer is horse, and AI guess is it was a horse is 8 times. And the darker the color and the larger the number on the diagonal, the more accurate the model. And what about the remaining squares? Those are minor mistakes that AI takes. Look at the accuracy dog column. It guessed correctly 10 times, but it misjudged it as a cat 2 times. This square. This makes perfect sense because cat and dog both have 4 legs and furry hair, and the AI sometimes get them mixed up. Through this matrix, you can clearly see which category of your AI constantly winning and which category is prone to misjudging. So mastering these two graphs is like mastering automated decoders for evaluating AI's competitiveness. Alright, so we have reached the final stage of the first half after training the neural network on computer. How do we fit into the tiny chip like ESP32? About the size of the fingernail. So please look at the inverted triangle models diagram. At the top layer, which is our brain is as a fullest, is a native models trained on the computer using TensorFlow. At this stage, all models parameters and weights are calculated in float32 or 32-bit floating point formats. This format is offering extremely high precisions, but at the cost of numerous size, which microcontroller memory simply cannot handle. Therefore, if we want to successfully land on the ESP32, we must go through the crucial compression process. It's called quantization. This step is handled by Google TF Lite's conversion tool. Its magic lies in forcibly compressing and align the original huge 32-bit float point number into 8-bit integers or integer 8 format. So it is like compressing a high quality lossless audio file into MP3. Same, after the quantization steps, the model's file size will be reduced by 70%, which is the 4-time reductions. And this process speed will increasing very quick. And finally, we need to solve the language barrier problems because we know Python is a very high level language. It takes a lot of time to compile. So because the microcontroller chip don't understand Python code, we need to go through these steps to convert Python to C. We will convert the quantized shrunk int8 models into a pure C++ hexa array, or you can call it a hexadecimal bit array that C can understand. In other words, complex models that originally had millions of lines in Python will ultimately become a long, straightforward arrays of numbers in our embedded code. Through this process, from the original high precision float32 huge models through the int8 quantization compression of TF-Lite core tool, it is finally converted into C++ with a single click. So the hexadecimal array, this is an automated secret behind how we can integrate a deeply learning systems that originally ran on a computer into a hardware world of a microcontroller and make it run successfully. So let's jump into the real code session.